Welcome to Study Loop.
This is Chapter 22, Problem 18 from Sears and Zemansky's University Physics. The electric field, 0.400 meters from a very long uniform line of charge, is 840 newtons per coulomb. How much charge is contained in a 2.00 centimeter section of the line? All right, so the very first thing I have done is I've drawn the line representing that the charge is along. And this is just a very straightforward application of Gauss's law. I'm going to draw a Gaussian surface that contains this line of charge as its axis. So you can see I've drawn this cylinder. The cylinder is going to have radius 0.400 meters because that's where that's the point I'm interested in, is away from this, where that's the value for the radius for the Gaussian cylinder that I've drawn. And we're interested in a length of 2.00 centimeters. I want to make sure I'm working in SI units, so I want to convert to meters, so I convert that to 0.0200 meters. So that's the total length L that I am interested in. Then I just use the definition of electric flux, because in order to use Gauss's law, I need to get the electric flux. So the electric flux, the basic definition is the electric field multiplied by the surface area times the cosine of phi, where phi is the angle between the normal to the surface and the electric field. In this case, because I've drawn a cylinder, the electric field is going straight out of the surface of the cylinder, so the angle between the electric field and the normal to the surface is just 0 degrees. The electric field is directly along the normal to the surface, so we don't need to worry too much about what this angle is. The surface area of the sphere, we're looking at the outside of the cylinder. So that surface area of the cylinder is 2 pi r times the length of the cylinder, which is L. And I use the lowercase l here and then a capital L here. They're the same length of the cylinder. So I made a substitution for the surface area of just 2 pi r times L. We don't need to worry about the end caps of the cylinder, so that would be the front end and the back end, because there is no electric field. The electric field goes out of the side of the cylinder, not into the cylinder. So we're only worried about the surface area just on the outside, not the end cap. So that's all that matters. So make that substitution for the surface area, and then we also just have the electric field, and that's given to us at this value. So the total electric flux then is 840 newtons per coulomb times 2 pi times the radius of 0.400 meters times the length of the cylinder, 0.0200 meters, multiplied by the cosine of 0. Cosine of 0 is just 1, so we don't need to worry about that too much. Plug this into the calculator and we see that the electric flux is 42.2 Newton meters squared per coulomb. So that's the first step that we need. Then we can use Gauss's law. Now that we know what the flux is, well, from Gauss's law, we know that the net electric flux is the total enclosed charge Q divided by epsilon naught, where epsilon naught is our universal constant of 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. A little bit of algebra, rearrange this to solve for Q. So we get Q equals the flux multiplied by epsilon naught. We just solved for that flux of 42.2 Newton meters squared per coulomb. So we plug that in for the electric flux, and we plug in our constant epsilon naught. Just multiply these together, and we get that the total enclosed charge is 3.74 times 10 to the negative 10 coulombs, for the total amount of charge that must be along this line, because that's the total amount of charge that is enclosed within the Gaussian cylinder.